Maybe doing good. I don't know. Maybe you need to ask Kate.
I could ask him directly. Right? He went to a different school.
Yeah.
I know what's going on. He plays guitar. So.
Oh, you know him, right?
He came to my house one time. Okay. We did a Thanksgiving and he came up and he was cool. Okay. Let's get back to our example and we'll actually run some code this time. And then I'm going to try to tell you some of the theory and sprinkle that in. That's called the detailed balance equation. And there's something built into this equation that I'm going to tell you about, but I'm not going to explain too much detail. But this is the thing you need to do to verify that an MCMC algorithm works and will converge to the right thing. So our example, just to remind us, it's xi's are coming from mu and phi, and we want to sample from its posterior distribution. So that we've got the likelihood formulation in this statement. You tell me the sampling distribution, I know the likelihood. And I have to come up with some priors. So I think the priors that we'll use are pi mu proportional to 1, pi phi proportional to 1 over phi. And you should always be thinking about what are your reasons for your priors, and you probably want more than one good reason to pick priors. We've kind of established that so far. We'll give you more good reasons for these priors soon. They're both Jeffrey's priors as well. They're both reference priors. So our posterior distribution looks like this. So phi to the n over 2 minus 1, the minus 1 is the prior. E to the minus phi over 2, sum of the xi's minus mu squared. So we know that's our posterior distribution, and we want to understand that joint relationship of phi and mu and how it depends on the data, and that's what a Bayesian's giving you. So I like that answer. And I like trying to express the joint relationships of parameters. That's probably the biggest place where you can win in statistics these days, is if you do everything marginally and you just come up with point estimators and you understand their variability only marginally, you're going to be beaten by somebody that understands it jointly, that relationship. So they can kind of tailor the contours of that distribution. As data sets get bigger and bigger and bigger and bigger and bigger, maybe things start mattering a little bit less. But in complicated scenarios, how big things would have to be, and in high dimensional spaces, things would have to be extraordinarily big for all this stuff not to matter. So everybody talks about big data and just being able to store it and access it and compute on it is the big deal. But it's sometimes not that big with relation to the space that it lives in. And so we have to understand all of that. Okay, so our posterior distribution, we want to learn about it. Here's a Gibbs sampler. And on your homework, you can implement this Gibbs sampler directly. But in my example, I'm going to bury in Metropolis-Hastings steps so that you can understand what an MCMC algorithm is really doing. So what you do is you update mu's. They come from its full conditional distribution. So this thing that we were computing early in the class, and we said it's a bit of a fiction, that why would you understand mu but know what the variance is? Sometimes we think about that. In Stat 101 classes, they have you teach that and learn about it all the time. But this seemed like even more fictitious, this full conditional distribution. But when you're Gibbs sampling, you use these full conditional distributions. They're usually easy to work out. And so we're not integrating anything, we're not doing any math, we're just writing down what that distribution is, and we're going to try to sample from it. If you didn't know how to sample from this and you didn't know which distribution it is, you could use a Metropolis-Hastings step right there. So you could use Metropolis-Hastings I would point out the way we're going to use Metropolis-Hastings right here, it's just for educational purposes. I'm going to use a normal proposal to walk around the space to show you what these proposal distributions do. But since this is already a normal distribution, it's a little weird to do that. Hopefully you can appreciate the rationale of why we're doing it, just so you can understand how an MCMC converges. What I'm actually going to do with this in this step is I'm going to tune it poorly so that you can see it converging. So, and then you can use MCMC, Metropolis-Hastings here as well. So when you bury in Metropolis-Hastings steps into that, that's called Metropolis within Gibbs or Gibbs with Metropolis. So you can say it both ways. Very common sort of thing to do. You could use Metropolis-Hastings and block update these parameters. And so let me just write down what that would look like. So here's a block updating procedure where this is sequential in nature. So Gibbs samplers are sequential updaters. And how you block everything is kind of the name of the game. In this case, I can't reduce that any further. So let's say I had a 50-dimensional space. I could block update 25 of the parameters together, and I could block update the other 25 parameters together. So, and I would do those in sequence. So that's a possibility as well. This is all up to your creativity. And the whole idea is that you pick a proposal that at least steps you around the distribution in some sensible way. You don't even have to be that sensible for it to work. It just will take longer to run since it's an iterative algorithm. So here would be like a block update. So I would do 4t goes from 1 to cap t. And what I would do for my Metropolis-Hastings is I would have a proposal, mu star, phi star. And these would come from some proposal distribution, g mu, g phi. So that's going to be our proposal. Of course, there's always the question, which proposal did you pick and why? So here's one way you could do it. I could end up letting this be g mu and phi. I could write down something like this. Maybe I don't have to think about their joint relationship because I don't really know what they are. If I knew how they were jointly associated with each other and I got something perfect, I'd probably be able to sample from this distribution directly. So step 1 is our proposal. Let me just ask a question. What would you pick maybe for this part of it? So if we're going to try to propose mu, mu can live anywhere. So what might be one strategy? It doesn't have to be right. It doesn't have to be great. It just has to be valid. T, maybe a T. Yeah, maybe a T. That sounds pretty good, and there's good reason to think maybe a T-dist would be good because it's heavier tailed than the original distribution, so you're making sure to cover those tails. So you're not going to isolate yourself just to the mass and not learn about the tail behavior. I think in stats, one of the fundamental things is to understand tail behavior. So that you can calibrate variability correctly. I think if you're not thinking about that, you're not a statistician, you're something else. So a T-dist. So maybe, yeah, I think that's fine. How would you center it? Which T-dist? There's stuff in here, right? It's up to your creativity. If you don't have it, that's too bad. Your technical skills won't get you there, but your creativity might. Sam, any guesses?
At the previous location.
At the previous, oh, I like it. I like it a lot. Cool. So maybe you would take mu t minus 1. So I guess there's some degrees of freedom in here as well. But maybe I center it where I was previously. It's kind of a good idea. So that means that if I had sampled a point in that area, there's mass in that area. So that's kind of a what have you found lately sort of proposal. We call those localized proposals. And so mu t minus 1, and then there's some scale parameter in here. I'll call it psi. That's the scale. And typically you would tune that. So how far out from where you were previously located would you want to propose? And then you would pick some degree of freedom right there. And that might be something you tune as well. So I will point out, since we do know that the margin on this is normally distributed, sampling from a t is slightly more complicated than sampling from a normal. So in terms of like it's sensible, it would probably work pretty well, but you know, maybe that's what you want to do. I kind of like the idea that it also has good global behavior. If you pick nu to be 1 and it's a Cauchy, I could at least jump far away every once in a while. And that's kind of a principle too. So the hard part about searching a space is you don't know where the answer is. So you kind of know where you found good answer. There's stuff around you, so you've got this local concentration that you would want to explore. But you also know you might not have learned about the entire space, so you want to jump away. So you want to do these two things that are at odds with each other. And kind of a T does that. What about this one? The precision. Again, it doesn't have to be a great answer, it just needs to be sensible so we can talk about the issues. Any other guesses from somebody that's not named Sam? I guess there's another Sam in the room. Sam too. Sam soon. What do you think?
I guess it's gamma.
I like it. It's sensible, right? At least it's positive. So if you said a T right there, it'd be like, oh no, that's not a good answer. So because T's can go negative. So maybe some sort of a gamma. And then I'm going to ask the equivalently hard thing, what do you plug in right there for that? And that might be hard. You might take alpha and beta and concentrate it somehow around where you were last time. It'd be a little bit weird to do that, and you'd have to understand the variability inherent to that parameterization. And so you've left with kind of this question of how do I do that? If I kind of knew what the variance was in the first place, you could pick choices that were reasonable. And since you're able to sample from a gamma there, you'd probably be able to do it directly right here. So it's a reasonable choice, but probably not super practical to do that. But it would get your homework up and running. So okay, so maybe. We'll come back to this question, but at least both of these are sensible, and it would make the code run, at least if I pick values that kind of put me, you know, somewhere around the space. I could pick really warped values right there and always be jumping outside of the target area and never really hitting, and it would converge super slow. So I would say since it's a continuum and every value is likely that it's possible to happen, theoretically it would converge. But if you picked really bad values because of the numerical, the discretization that our computer does in the rounding error, you can make it so it never actually worked. So that's the name of the game in MCMC, is how do you pick these choices so that your algorithm converges fast. And then you do this acceptance step. So I compute the acceptance rate. This is min 1. I would look at my target right here. That would look like pi mu star phi star given x divided by pi mu t minus 1 phi t minus 1 given x. And then I have to incorporate my prior structure. So I pick this g mu phi. I'm just going to save space by using that notation. However, I pick these. Proposal downstairs, where I was last time upstairs. The detailed balance equation is going to show this is the right rule. So far we've just kind of explained it in an intuitive level that kind of makes some sense. So, and then I would update accordingly. This is going to be one of two things, mu star, phi star, my proposed location. This will happen with probability alpha, and mu t minus 1, phi t minus 1 would happen with probability 1 minus alpha. And we run this thing, and it will eventually converge to something, assuming you don't have any numerical errors, assuming that your proposals are at least reasonable. They put stuff in the valid part of the space. Okay, so that's what a block update would look like. So I'm going to walk you through this with pretty clunky proposals, and I'm going to make them intentionally clunky so that you can watch the trajectory of convergence. When you do this on homework and you sample from these directly, regardless of how you initialize that, that's the only thing you need to initialize. So anything that you're going to plug into this, you need to initialize it first. But whatever you pick, it's going to converge in like 2 steps. And so if you're the person that sends me the email and say, what's wrong, this works way too well, I'm going to know you're the one that wasn't listening to this. Happens every year. Okay, let's look at the code. I love this. And I love it not just for the inherent beauty of an algorithm and that I think it's cool and I like thinking about certain strategies because it teaches me about philosophies. So I think that's what we do in life. So I do think that. But I like it because I could build a more realistic model for something and start layering in hierarchies into the model. And you might say, well, I don't know how to do the integrations, or I don't know how to do the math. I'm not sure what distribution I just formed. It's totally unique to the problem. And if you did that, and you made a more realistic model, and it worked better, you could use something like MCMC to estimate it. There are other approaches. So the only downside to MCMC is it's iterative. It takes a long time to run. So there's other things you could do. If you guys are into things like variational Bayes, if you know something about it, that's using the EM algorithm on a approximated distribution, a factorized distribution. I might say what that is later in class, but not now. You could use that to seed your initial starting points and then feed it back into a Metropolis-Hastings sampler and refine that answer and understand variability. So you could do things to speed this up. And I think that, once we've kind of carved out the general theory of things, we understand how flexible it is, the next step is always to speed it up. And that's probably where the field is now. So how do you parallelize everything to make everything super quick? Okay. Let's look at the code. So there's just a couple things in here. Can everybody see the code? You guys can all read it? Do I need to make the font bigger? I used to do this with like 10 fonts. So I think this is 18 or 20. Okay, so I've got this thing, Gibbs second example. My first example is a block updating example, but I like to tease it all apart so that you can see the full-blown glory. So this is your first example, but in my head, it was my second example once upon a time. I've got some basic functionality controls that I want to plot the trace plots, and the trace plots is plotting the trajectory of everything. And sometimes I like to turn them off, so I'm just plotting the traces as we go. I'll point out that that might feel really good to you, and I've seen people running I/O out to their screen after every iteration or updating plots after every iteration. And they're like, why is my stuff so slow? And so printing and pausing and collecting everything and outputting is about the most expensive thing you can do on a computer. So sometimes you want to turn that off after you have things reasonably debugged. Thinning is, my thinning step is 1, which means that you're not thinning. So in your trace plots, and we'll look at these a little bit later, they're auto-correlated because it's a Markov chain. And so you're not getting IID samples out of everything. So if you wanted to mimic the behavior of IID samples, one approach is to, instead of collecting every sample, you collect every 100th sample. And it'll take out that autocorrelation. So if you have something that's kind of moving and it's kind of associated with itself, the farther you move into the chain, the less it's associated with previous draws. That's kind of just like even that auto-regressive model. So autocorrelation, they're the same words for the same reason. So you might say, I want IID samples from this thing that the histogram, it looks like the approximation I'm trying to come up with, but the sequential values are autocorrelated. And that might jump something up. So you can do one of two things. You can grab every 100th sample. So if I wanted to do that, I'd make my thinning step 100. I want to look at every sample so that we can see the autocorrelation. So I usually build in a toggle to do that. But I could also do another thing to take out autocorrelation. So let's say I have a sequence of values that come out of this iterative scheme, and it well approximates the histograms will approximate the distribution, and I didn't want to throw anything away. How would you rip out the autocorrelation from something that's heavily autocorrelated? Say I had something like this. So this is T. So you can kind of see it's like converging to something. It's like in this band. But to learn about all these other areas in here, I'd need more samples. Let's say I ran this for a really long time. And my target looks like this. And my histogram looks pretty close. And for some reason, I think I've converged. But I wanted to use these samples in an IID fashion. And they're not IID. You can see the little snaking pattern in all of this. So one thing we could do, we could thin. So I could grab that. I just need the same systematic rule. That I'm going back and I'm taking a random sample from a sample. A random sample from a sample is still distributed according to that sample. So I'm going to uniformly sample from my sample. So that's what it means to uniformly sample from something. So I can grab all of those. There's a downside to it is I lose a lot of the samples that I have. So I need to run it longer. So what's another way I could take these samples, turn them into IID draws, and the histogram would stay the same? Shuffle. That's it. Shuffle. So in one of my papers, that's a very important step is you do the shuffle step every once in a while. It saves me from doing a ton of that. And it works great, and it's super easy to do. So you could shuffle. One of the downsides to MCMC sometimes is you need to run it for a long time to get it to converge in a complicated space if I had bad proposals. So you can run it for a long time, and so I'm accumulating this huge collection of values in RAM. Maybe I'm writing them to file, but at the end of the day I have a terabyte file or something like that. It's not that bad. So thinning can also alleviate the need for storing so much stuff if you have a slowly moving chain. So it's just a practical thing so you don't blow out your RAM. So that'd be the reason you would thin. So it's not a theoretical thing. It's a practical thing that you do. So usually in papers that run MCMC, they'll tell you how many thinning steps they've done and blah, 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 blah. And I don't know, I kind of find it a little bit juvenile, but people like to do it. So I thinned this much, I ran it for this long, and then my burn-in was huge. I don't know if any of that's any good. I trust that you know how to run this stuff, and you're able to give me real diagnostics instead of proxies for diagnostics. Okay, number of the step size, that's gonna be my proposal variances. So it's gonna be, so I can slow this chain down. But let me tell you which proposals I'm gonna use right here so that you understand that control. So here's gonna be my proposal for both things. They're similar, but they're a little bit different. So my proposals, are gonna look like this. I'm gonna use Sam's idea, but I'm gonna use it from a normal distribution. Lots of good reasons I like the T thing because of the heavy tail. But we're going to make it a little bit simpler. So I'm going to center this where I was last time. And I'm going to have some proposal variance. I'll call that psi squared for mu. So this is a tunable. And so that's what that 0.1 is. So I'm plugging in 0.1 there. So basically I'm saying I want to tippy-toe around the space. So, and learn about it. If I made that number really big, I'd be taking these huge leaps through my space. And so you can kind of see the Goldilocks phenomenon. And so that it's like you don't want it to be too small and you don't want it to be too big. You want to be able to explore your space fast, but fast enough. So, and then I'm going to do something like this. Is normally distributed phi t minus 1, and then I'm going to have some variance here for phi. That's also going to be a tunable. And I know what you're thinking. That's not right, because this could go negative and the precision has to be positive. So I'm going to do something really easy. And I'm going to plug in an indicator function that says phi is greater than 0. So this is an indicator. If you want me to use the delta thing, that would be delta. So that just means it's a 1 if it's positive, and it's a 0 if it's negative. And so if phi were negative, you're putting 0 mass on that area, so you would never sample from it. How do I sample from a truncated normal? So this is called a truncated normal. Any ideas? Sampling is up to your creativity. So if you're really creative, you can write whole textbooks and make a career out of sampling. Keep in mind that is what all statisticians are doing out there in the real, all scientists are doing. They're going out and they're sampling. And they're trying to sample uniformly from that population and get it right. They might have to stratify and sample uniformly from different strata to make sure that they've got certain groups represented in their sample. So it's the exact same thing. Everybody does. We can just do it on a computer. How do you sample from a truncated normal? So a truncated normal looks like this. I would be sampling from phi centered at phi t minus 1. There'd be some variability right there that I would control. So it would control how far away I'm from this. But I would be taking this part, this 0, and getting rid of it. And then I would raise the height ever so slightly for that right there. So I'd need to raise that thing up so it integrated to 1. So I just need to change the normalizer. That's an important thing. You need to change the normalizer a little bit. That's a key to what's wrong with my coded example. It's so barely wrong that you can't really notice in this example, but we should probably get these things right. So how would I sample from this distribution?
Find its density and divide out the mass.
Okay, so I do that and I write down the density function. And you could write down the density function, and you would have to have some cumulative normal distributions that you'd subtract off of things to get the normalizer right. We'll look at that in a little bit. That's what Wilkinson's paper was about, or his article. So it shows you exactly what the answer is, how to fix it. So, okay, you write down the density, and then what?
You divide out the
Cool. How do I get a sample? How do I sample from it? I get what it is, and I get how you renormalize it, and I get what the density function is, but just because I can write down the density doesn't mean I know how to sample from it. It's a confusing point at first. We can write down the function, but we don't know how to sample with densities proportional to the area under that part of the curve.
Can we just sample from a normal distribution and drop the negatives?
Yeah, that's it. So grab from normals, and then when it goes negative, just throw them away and do it again. So the mass, the frequency of this stuff would be strictly proportional to the height of that curve still. So you're still getting it from the normal. So if I see that stuff over there, I just throw it away. Does anybody know what you call that kind of sampling? Rejection sampling. So we just reject the invalid things. So you can sample from a space that has its support that isn't along the whole thing and just throw away the other stuff. You can't do it in the other direction. If you sample from too small of a region, you'll never be able to extrapolate that out. So you rejection sample this thing. You could call it accept rejection. So that's an algorithm. Some people call that envelope sampling as well. And so I think when they taught me about sampling when I was a senior in high school, they taught me that. So it's true. So I estimated pi by dropping a pencil on a circle. You ever seen this experiment? And then you count how many times it gets inside the circle, and you throw away, you look at the number of times you dropped it, and then you look at that ratio of points that are inside the circle compared to how many times you've dropped your pencil. I don't know if you've seen this. We can do it later. It always ruins one of my pens. So, okay. So, but I think that kind of makes sense. That's how you do it. Okay, so back to the code. We're going to use this sort of normal proposal. So that's what that step is, and you'll see this kind of buried in here. There's iterations. There's my burn-in period. We've talked about burn-in, the stuff we're going to throw away. Let's just make our burn-in really small. We don't know what the burn-in is yet. So let's just pretend we don't know. So we'll run it some number of large iterations. I could run it longer, but usually this will get me there. It might not be sufficient depending on what my step size is, how far I walk through it. So if my step size is small, it might move through my distribution at the right rate, but it's going to burn in slower. So there are adaptive schemes that start with a large step size and then adapt and make the step size smaller and smaller and smaller. So you're not supposed to change the functional form of your proposal, but if you're just going to throw away the stuff in the burn-in anyway, you could change it. So it's junk to you. Who cares how it's distributed? So I have starting points. I'm going to try to start far from the true answer. I could plug in my true answers right here, but that would be a bit cheating. So I'd like you to see that how does it work if you didn't know what the answer was. Here are my priors. So 1 over phi is the same as 1 over sigma squared. You can do the transformation and show that those are equivalent distributions. So create space for everything. So I like to pad everything with zeros up front. So I know what the computer does if I don't do that. So it starts trying to allot memory dynamically. So if you start with just one cell of something that you're going to try to store, and you try to collect another value in that array, it's going to write a new array with that slightly bigger space, take the stuff out of the other thing, copy it over, and delete the other thing. So it uses twice as much memory at every step, and it's really slow to do all that rewriting. You could come up with a linked list formulation for it, if you guys know what that is, but those are also pretty slow in the way computers allocate memory, is that it attaches an address to everything. And so if you're building a linked list, the addresses aren't in order, and so the way that everything gets accessed, it uses those numbers to pre-anticipate what you're doing. The compilers are really smart, or the interpreters are really smart. So padding everything and putting it into an array if you can will speed up your code tremendously. So it's not that bad at the very beginning, but as it starts running for a long time and those vectors get bigger, doing the memory swap is pretty expensive. So again, it doesn't matter for your homework, but it's nice to just get this stuff right. I initialize, so that's my initial point. That's what I'm grabbing from upstairs right there, and I'm plugging it in. And then I have some plotting. I'm going to plot where my initial step is, and then I'm going to run this algorithm. So this is a Gibbs sampler. This is really using an embedded Metropolis-Hastings sampler. So more on that later, but I think we filled in a lot of those steps. So we'll run this thing starting at 2 because my initialization starts at 1. And here's what we're going to do. We're going to propose. So I'm going to propose using that proposal I wrote down. That's this. So I have a random normal times my step size. So I guess that was actually my proposal standard deviation, since I'm multiplying that in. So my proposal variance is 0.01. It's pretty tiny. And then I'm going to recenter it at where we were last time. That's a good suggestion. So algorithms should search around what you found, but they should be able to jump to other places. If you were able to write down that function, and if you were really savvy at recognizing things and saying, I know that's unimodal, and it doesn't need to jump far away. There's only one mode in this distribution. I'm not going to get trapped anywhere. Then using localized proposals is a good idea. If you have things that bend in funny ways, maybe this isn't the right schema, and if you have things that are multimodal, where the modes are very well separated, this wouldn't be a very good scheme. You would need a different MCMC approach. That's what MCMC books are all about. Okay, I have everything done on a log scale so that it will work. We'll look at it when it's not on a log scale. What I mean is I put it back on a log scale using this green stuff, where I just kind of took the product of everything, built my likelihood using a product that's numerically very unstable. The product in your code, you really want to turn everything into sums. Logs do that, products. Logs also take big stuff and it makes them small. So computers enjoy that. And it takes small stuff and it makes them bigger. Computers enjoy that. There's a sweet spot in there. And so this oldie but goodie 1960s trick of taking logarithms of things is still a very good idea. So we're going to take logs. What I don't mean is I take the log of something that's this big product, because this is going to miscompute everything, and when I take the logarithm of it, it will not fix it. So this right here is numerically much more stable once I take the logarithm of everything. Let's just look at this. This I'm saying is the log, this is where I'm proposing to, so I get my proposal value and I plug it in right here. So I've got my x's. I could have used probably x bar for this step because phi is considered fixed, but I didn't. I still use it in the summation formulation. So that's just the sum up in the exponent. I don't have the square root 2 pi, and I don't have the leading phi n over 2 minus 1 in here. Do you know why I don't have it? What's that? Yeah, so if that step B is fixed, and so phi is going to be the same, so if I took a ratio, they would cancel out. On a log scale, we're going to take a difference. So a log ratio, the Metropolis rule comes in the form of a ratio, this thing right here, and it is going to subtract off that phi. So I don't even need to write it down. Can anybody see what happened to my proposal distribution in this? So So I have my currently at and my proposed at, and I'm going to take the, since this is already on a log scale, I'm just going to take the difference. This isn't a ratio, it's the log ratio. So don't be tricked by the naming convention. So it's the log ratio. Can anybody see what happened to my proposal? So it's supposed to be in there. So all I have right here when I take the log ratio and I'm subtracting everything is I've just got this part of everything. Hopefully people can see that. Pi mu given vt minus 1 and x. The log of this thing is going to be the log of 1 over 2 pi, I'll say v t minus 1 to the n over 2 minus 1 and all of that. I could have this part of everything. I could have buried in the prior if I wanted to. I don't even need it in any of that. But this is going to be e to the minus v t minus 1 over 2 sum of the xi's minus mu squared. So all we're seeing in this is this stuff right here when I take the log. In both the proposed and that, they have the same phi values. This should be, oh, this was for the block sampler. But for the Metropolis within Gibbs, the phis are the same at that step, so they'll cancel out. So all I have right there is this thing up in the exponent. Speeds up my code, makes it stable. Where did my proposal go? So I'm not using it in this step right here. It's not incorrect. Can anybody see? This is where it went. So we see the target ratio or the log ratio, but the proposal ratio right here, if I ended up having g phi given mu t minus 1, this is the way I'm encoding it. So instead of writing down just g mu, I'm going to condition on mu t minus 1. So it's a conditional formulation of that distribution. So this thing right here is equal to whatever my proposal variance is. The root 2 pi's won't matter. You see that in the ratio, they'll cancel out. I've got my tuning sort of thing. E to the minus 1/2. I've got my psi squared mu down there, and then I have mu star minus mu t minus 1 squared. So that's what my proposal looks like. Let's look at the reverse proposal when we go in the other direction. So our other direction, the reverse proposal looks like this. T minus 1. If I'm going to go back to my old location, given mu star, this is going to look like, let's get rid of that part. We don't need it. Let's just look at the kernel, e to the minus 1/2. This has the same variance. If I'm going to move back the other direction, I would have to propose in the backwards direction. And this is mu t minus 1 minus mu star squared. This is that. So when I take the ratio, bless you, when I take the proposal ratio, the inverse proposal ratio, they cancel each other. There's a symmetry to them. That's called a symmetric proposal. So symmetric proposals cancel out in the ratio. So that's an example of a symmetric proposal, and it's going to cancel out in the ratio. So over here, for my Metropolis step, I'm going to have min 1, and then I'm going to have pi mu star given phi t minus 1 x divided by pi mu t minus 1 given phi t minus 1 x g mu t minus 1, so just a little bit more room, g mu t minus 1 given mu star over g mu star given mu t minus 1. So we're using the previous value in all of that, but in terms of the proposal, that's going to be 1 right there. So symmetric proposals have that ability. Darren Wilkinson's blog talks about this. This is the mistake that I'm making in the variance step. So when we see this in the variance step, because that normalizing constant changes depending on where you recenter it, i.e. that little tail gets fatter or smaller, you need to build in that normalizing constant, the ratio of it. It's usually close to 1, which is why you can't tell. So in the code, like Darren Wilkinson walks you through that. So please read that and it'll give you all the heads up. Another thing you could do is I could transform log phi into log phi. Or I could talk about some other parameter that's the logarithm of phi. And so if I did that, then that would take on negative or positive values and I could use a symmetric proposal there. So if I transform the problem, I'd have to do a little bit of math up front to figure out that Jacobian term. So that's what this is right here. So I take the ratio. Keep in mind, if I want to accept with probability whatever that ratio is, I can just take a random number and check to see if it's less than it. But since this is on a log scale, I have to take a logarithm of that random number. So this is called inverse CDF sampling. So if you don't recognize that, we can talk about it a little bit next time. So it's just inverse CDF sampling for a Bernoulli distribution. It's just a Bernoulli coin flip. So that's how I always code it up. I also don't have the minimum of 1 in all of this. And the reason why is because if it's 5, I'm going to accept it. So if it's bigger than 1, I always make the acceptance. So it'll accept. So log rand is less than my log ratio. Will accept if it's bigger than 1. So I don't do the pre-compute on min 1 because you don't need to do it. So it's just for the theoretical part. And when we go through detailed balance the proof, we will use it there. I do the same thing down here. And I make a note that this isn't actually a symmetric proposal, and I've treated it as such because I've done the exact same thing down here. So look over that code. So this ratio needs a correction. So you don't need to send me the correction, you'll do it for homework. So Darren Wilkinson, blog on the course webpage, tells you all about it. So it's a good write-up. Okay, some number of steps, I plot everything, and so this is just plotting. So let's run this, and then next time when we come in, we can pick up with running it, tweak the code, try to break the code, see what the numerical stuff is all about, and then I'll tell you the theory. That is this. So same example that we had last time, I didn't clear my cache. It's the same stuff, I'm just gonna run everything. And the only place I use the truth is in plotting. So bing, there's my truth right in the middle of everything. And then I started running up here. It converged, and it got down here and it converged into something. And if I gave this as an answer, this would be a really bad answer. So I've also plotted the marginal distributions of everything right here. That's it for phi. We'll look at these closer next time, and that's it for mu. And we'll talk about these plots as well. That's what's called a trace plot. So I'm plotting those trace plots. So this is a bad answer because I have all the burn-in built into it. And so what we want to do is rip out the Burnin. And we also want to stress this code and see if we can break it. And so as it's written, it can do anything. So, but if I took out that logarithm stuff, it would probably not work for bad starting values that are far away from the truth. Just keep in mind in all of this, if I have a previous location that's very far from maybe what I'm proposing, or maybe it is far from the truth, it's actually in this part of the step, because I don't have it written down. We'd have to go back, write down that math again. But if your starting values are far from the truth on a non-logarithmic scale, and they get squared, and they get exponentiated, it blows up your group. I think you understand the metaphor. It doesn't physically blow up, but it doesn't do things right. So let's come back next time, and we'll just focus on the practicalities. And if you're bored, we'll do math after about 15 minutes of running this. Thanks, you guys. That's it for now. I'll see you on Friday.